Okay, so welcome back. So let's see. I was asking chat. To do an example of a problem with level surfaces when c is equal to some number. Yeah. So at the end of last class, I had written this fact out, which says that every graph of a function of two variables can be realized as a level surface for some function of three variables. So actually, if you're thinking of graphing any function f of x, y, you can think about that as a level surface. So basically, any function of two variables you can think of as a level surface. So there are tons of examples of these, but I can give you an example, of a level surface, for instance, let's just pick some g. So it's actually not even given to us as an f here. But it is given to us rather as a, we'll say, here, let g of x, y, z be x squared plus y squared plus z squared, right? Okay, so what is the level surface g of x, y, z is equal to 4? What is this? So this is a level surface for this function g. What does this look like? Well, it's a sphere of radius 4, right? So if I just write this out, this is x squared plus y squared plus z squared is equal to 4. Or sorry, it's a sphere of radius 2, not 4. So this is sphere of radius 2. So if I write 4 is 2 squared, then you see that this is my normal formula for a sphere centered at the origin in space. Right, so this is sphere of radius 2. Okay, and of course, the reason why I wanted to think about this as a level surface is this is where I'm headed, right? So, oh no, my paper from last time got wet. Well, that's okay. So for last time, you see my wet floppy paper here. So from last time, I saw that if I had a function of two variables, and I set that equal to a constant, that was a level curve, right? So there's a curve in the plane. And as we saw last time, the gradient vector of this function at a point was actually a vector normal to the graph of this level curve, okay? Which means, as a normal vector, it specified a tangent line to this level curve. Now, just bumping our dimensions up one. The idea here is that if g of x, y, z is or defines a level surface, g of x, y, z is equal to some constant. Okay. Then I can use the gradient of g at a point x, y, z to define the tangent object to the level surface. G of x, y, z is equal to constant. Okay. Now, of course, the reason I'm using the words tangent object here is because tangent lines, as I mentioned before, that's not going to be good enough, or I shouldn't say good enough, it's not going to be the thing that we're actually interested in, because it's just not enough dimensions, right? So the tangent object of interest is always going to have the same dimension as the thing that it is tangent to. Okay, so bringing back my picture of level curve, a curve is one-dimensional, yeah? It might take the plane, which is two-dimensional, to graph this curve, but a curve itself is one-dimensional, right? There's only one direction you can go. You can either go this way around the curve or the opposite direction, right? Which we count as being part of the same direction, right? So there's one axis of motion you can travel around a curve. And so the tangent object that we care about to a curve is a line, which is also one-dimensional. Okay. All right. And so the idea here is that if we have a level surface, then the tangent object to the level surface is going to have the same dimension as the surface. Well, a surface has two dimensions, right? Even if it takes three dimensions to graph this thing. Or if you think about a surface sitting in three dimensions. Regardless, a surface itself is two-dimensional, and so the tangent object itself is two-dimensional. And as we'll see, this is going to be the tangent plane. Okay, what's the idea here? So the tangent plane is going to be our object of interest for this entire lecture. It's actually kind of the reason for defining all of this stuff anyway. So the idea is, let's say that I have space, okay, and in space I have some surface, right? And maybe my surface is even something that is not the graph of a function, right, of two variables. So here's an example of some ellipsoid thing, right, a football. So here's my ellipsoid, okay, sitting in space. So this is not the graph of a function because it fails the vertical line test. So this can never be written as z is equal to f of x, y, z, right? So if you try to say that this is the graph of some function of two variables, well, you're wrong because it can't be, because there's ambiguity here, right? So for some x, y, there would be two values. This thing would be multi-valued, and that's no good. But I can express this as g of x, y, z is equal to some constant. Okay. All right. So nevertheless, I want to discuss, well, what happens, say, at this point. Right. So at this point, right, which is some point in space, I'll label x naught, y naught, z naught. So at this point that is on this level surface, I want to talk about the tangent object. Well, as I mentioned, I could draw in a line here, right? But I couldn't just draw in one line. I could actually draw in infinitely many lines here that are tangent to this ellipsoid at that point. Okay, so talking about tangent lines isn't going to do us much good. Instead, what is important is a tangent plane. Okay. So it is the tangent plane at this point that we are interested in, right? So this is the tangent plane. So this is the tangent plane to the level surface at x naught, y naught, z naught. Okay. Well, recall the material that we covered in chapter 11. Right? Chapter 11 told us exactly what we needed to write out the equation of a plane. Okay, so what pieces of info do I need in order to write out the equation of a plane? I need a point that the plane passes through. Well, I have that. That's this point. And then what's the other thing that I need? Well, I need the normal vector, right? I need the normal vector to the plane at that point. Okay. Well, here's where this bit of info from last time comes in. If we go back now from level surfaces to level curves, right? So I have a function of two variables. It's equal to some constant. That defines a level curve. We saw that the thing that defines the normal object at a point is actually the gradient vector. Okay. And that's the gradient vector of f, this function of two variables used to define the level curve. So then, what do you think is going to happen when I have a function of 3 variables, it defines a level surface, and I need to come up with the tangent object. Well, here's exactly the point. So here's the very important fact. Okay, so let g of xyz be nice. Okay, means it has its first order partials. They're nice and continuous, so that the level surface we get is an honest-to-God surface and is also nice. Okay, so let g of xyz be nice. That means, again, as I said, it has continuous first-order partials, so it's first-order differentiable at least. And let sigma be the level surface. G of xyz is equal to c for some constant c. Then the gradient of g at x naught, y naught, z naught is the normal vector to the tangent plane to the surface sigma at the point x naught, y naught, z naught. Now again, you may say, wait, gradient involves these first order derivatives, right? I'm used to derivatives being associated to tangent things, but you're telling me that the gradient of g is normal, right? The better way of thinking about it is the gradient of g, while it may be normal to the level surface, the normal object is the thing that actually defines the tangent object, right? It's actually more efficient, right? Because we saw that to define a line in space, we needed a point and a vector, right? But also to define a plane in space, we needed a point and a vector. The difference being that the vector we needed in the case of the plane was a vector that was normal to every vector in the plane, whereas the vector that we needed in the case of a line in space was parallel to every vector. And so being normal, that gave you actually more geometric info. It was actually more efficient, right? Because technically, to describe a line in space and to describe a plane in space, it's the exact same amount of info that's needed. But because the vector that's cropping up in the description of the plane is normal, you're getting actually more geometric info. Okay, so this is the normal vector to the tangent plane to sigma at that point. Okay, and so let's do a quick example of this. So maybe I'll get a fresh sheet of paper so I don't have to change halfway through. So let's revisit that example we just did. Find the equation for the tangent plane to, say, the sphere of radius 2. That is x squared plus y squared plus z squared equals 4, i.e. sphere of radius 2, centered at the origin. At the point, well, let's see here. If x is 1 and y is, say, minus 1, then z needs to be square root of 2, right? So we'll say the point 1 minus 1 square root of 2. Okay. All right. And so, rewriting this, right, I can rewrite this as a level surface as I did before, where g of xyz is equal to x squared plus y squared plus z squared. Right? And so my level surface in question is g of xyz is equal to 4. This point clearly belongs to that level surface. Okay, that's actually how we cooked it up. So then my g in this case is x squared plus y squared plus z squared. So the main thing that I have is that the gradient of g at a point is the normal vector to the tangent plane. I already have the point in question, so all I need is a normal vector to be able to write this tangent plane. So I compute the gradient of g. So what is the gradient vector of g? Okay. Well, in order to write this, I need to write the x, y, and z partials of g. So what is the x partial of g? Well, this is easy enough. It's 2x. What's the y partial of g? 2y. What's the z partial of g? 2z. And so the gradient vector is 2xi plus 2yj plus 2zk. All right, so easy enough. All right, so then in particular, the gradient vector of g at 1 minus 1 square root of 2 is the vector. I'm just going to write it like this. This is 2 minus 2, 2 root 2. Okay. All right, so there's my gradient vector. So I have the vector that is normal to the tangent plane at that point, and I have that point. So the equation for the tangent plane, equation for tangent plane to the level surface g of x, y, z is equal to 4 at the point 1 minus 1 square root of 2 is, I have the components of the normal vector, then I have my point. So this is 2 times x minus 1 minus 2 times y minus minus 1, so that's y plus 1. Okay, plus 2 root 2 times z minus root 2 is equal to 0. If you're confused about where that comes from, just go back to chapter 11 stuff when we talked about writing the equation for a plane. Right, so the components of the normal vector, which we know now is the gradient evaluated at that point, are the coefficients of x, y, and z. And then the things that are in these parentheses here, right, I'm subtracting off the components of this point, right, x minus 1, y minus minus 1, and z minus root 2. Okay, so that's how to find the tangent plane to a level surface. Now, what we are typically interested in, of course, is not the tangent plane to a level surface, but it's the tangent plane to the graph of a function. All right, so typically, what we're interested in is the following. Right, typically, we're actually interested in finding the tangent plane to the graph z is equal to f of xy, right? That is to the graph of a function of two variables. Okay, but where does this come up? Well, it turns out, like I said, this is actually easier than doing it to a level surface. I mean, it's the same thing, and the reason for that is this fact from the end of class last time, that every graph of a function of two variables is a level surface. Okay, it's actually a simpler object, right? I mean, in fact, as we saw, right, this formulation would allow me to find this tangent plane at any point on this surface, and that's even if my surface looks something like this, which is not the graph of a function. This is a more complicated thing. Okay, but this same process will apply for a function of two variables, and the way that it works is, well, now I've moved my paper. So the way it works is exactly like this. The graph of a function, that's me saying the collection of all points x, y, z, such that z is equal to f of xy. Well, I can rewrite this, right? I can rewrite this equation, z is equal to f of xy, as f of xy minus z is equal to 0. Okay? But then I can just define g of xyz to be f of xy minus z. And so the level surface, g of xyz is equal to 0, is the same thing as the graph z is equal to f of xy. Okay, and so this is where your function of three variables pops up. Okay, and so let's do this exact same thing. Okay, so rewriting this as we do, so this is f of xy minus z is equal to 0. So if we let g of xyz be defined to be f of xy minus z, then the level surface in question is g of xyz is equal to 0. And now we can do the same analysis that we were doing before for our level surface here. What is the vector that is normal to my point? So at a point x naught, y naught, z naught. So let's look at a point x naught, y naught, z naught. What is the vector that is normal to the tangent plane to the graph of a function at x naught, y naught, z naught? What is z naught in this case, right? Well, of course, this is actually x naught, y naught, and z naught is determined by the functional value at x naught and y naught. So this is f of x naught, y naught. Okay. And so what is the vector that's normal to the tangent plane at this point? Well, I get that from the gradient, right? So I need to compute the gradient of g at x naught, y naught, z naught. But what is that? Okay, well, actually, let's just go component by component and compute this. What is the x partial of g at some xyz? Well, g is defined to be this thing. It's f of xy minus z. The x partial of g is, I take the x partial of f of xy, which of course is the x partial of f. And then in this term, I'm taking the x partial of minus z, okay, which is 0. So the x partial of g is actually just the x partial of f. What is the y partial of g? Well, again, I take the y partial of f. That's exactly the y partial of f sub y at xy. And the y partial of minus z is 0. So the y partial of g is the y partial of f. What is the z partial of g? Well, the z partial of f of xy is 0 because it doesn't depend on z. And the z partial of minus z is minus 1. And so these are the components of my gradient vector, right? Gradient of g here. And so what do I do? What do I say about this? Well, now this allows me to write out the equation of the tangent plane. So the equation for tangent plane to the graph of f x y, right, or z is equal to f of x y, at x naught, y naught, z naught is, the x component is the x partial of f, so this is f sub x at x naught, y naught times x minus x naught plus f sub y at x naught, y naught times y minus y naught minus 1 times z minus z naught is equal to 0. And so this is what I meant when I said this is actually simpler, because the component here is always this minus 1. Right? Now you might say, well, what if I had, when I had written this, what if I had written it backwards? So what if I'd written this as z minus f of xy is equal to 0 instead of this? You can definitely do that, and the only difference here was that you would have minus f sub x minus f sub y plus z minus z naught. So here we just have one minus sign instead of two. That's the reason for writing it this way, but there's no reason why we couldn't do it the other way just as well. And so this allows you to find the tangent plane to the graph of any function like this, okay? Following similarly, you can either just straight up remember this formula, or you can do this process every time, doesn't matter. But this allows me to find the tangent plane to the graph of a function. And this is what I'm interested in. This is my thing that is the analog of finding the tangent line, or the equation of the tangent line to the graph of any function in the plane, right, of one variable. Okay. Now, why is that important? It's important for a number of reasons. For this, like I said, for the same reason that finding the tangent line to a curve in the plane was important. But one of those is the notion of the derivative as linearization, right? So linearization is one of the reasons why this is important. What do I mean by linearization? One interpretation of what the derivative is doing for a function is that it is linearizing it. So what does that mean? The idea behind linearization is, suppose I have the graph of a function in the plane, okay? So it's this nice curve. Now in Calc 1 and Calc 2 land, how can the derivative be seen as linearization? The idea is that when I draw some points here, okay, on this thing, let's draw a few points. So maybe here's a point and here's a point. And if I draw in lines that are tangent to the graph at these points, one way of thinking about what's going on here is that we are not just finding tangent lines, but we're finding lines that are really close to the functional values for this function as long as we stay near that point. So I've just drawn in a bunch of tangent lines here. The idea is that if I focus my attention very close by these points, then each of these tangent lines provide me with values that are approximately equal to the values on the curve itself. Okay, what do I mean by that? So for instance here, right, I have this tangent line that is tangent to this graph at this point. So then what if I go out to this point? If I go out to this point and I say, is there some line, right, that has values on it that are very close to the values of the function near this point? The answer is yeah, that line is the tangent line. Right? In fact, all these tangent lines give you an approximation of values so long as you stay near this point. Right? Of course, by the time you've moved out here, this tangent line is now no longer close to the graph, right? But as long as you stay near these points and you consider the tangent lines that are tangent at those points, right? So each tangent line is associated to some point here. If you stay near the point it's associated to, the values on the tangent line are very close to the values of the function. Okay. So much so that if, in fact, I were to look at this same plot and instead of having the curve here, I just reproduced the tangent lines themselves, right? Now that's a bad job. Okay, so if we were doing this in person, what I do is I take eraser and I just erase the curve. I don't do this. But if I do this, what do you notice, right? What is this? Now I just have the tangent lines. I don't have the curve itself. But you can see that if you have the tangent lines, you actually can tell the shape of the curve, right? You can tell the curve does something like this, right? It does some turning and goes up here and, right, it does something like that. Okay, the idea here is I've basically taken my curve and which is a nice continuous smooth object, and I've replaced it with a bunch of linear things, right? I've turned it into a piecewise linear object. Why might I want to do that? Well, I mean, for computation's sake, right? This is more amenable to computation by computer than some continuous thing, typically. And in fact, in Calc 1 and Calc 2, you talked about this. This was the notion of linear approximation. Okay, and literally what that was was exactly what I just said before, looking at this point, or looking at some point on curve, and using the tangent line to the graph of that curve to approximate values nearby. Okay, so this is how you did it in Calc 1 and Calc 2. And so I want to do something similar. Okay, I want to do something similar here in the world of Calc 2. Now, what was linear approximation? What was, you might remember the formula off the top of your head. What was the idea? The idea was if I've chosen some, we'll call this x naught. So if I've chosen some x naught, right, then if I want to approximate the value of f at some x naught plus a little bit, right, the idea is that this h is going to be a little bit, then this is approximated by what? This is approximated by the value of f at x naught plus a little bit. What is that little bit? Well, it is the derivative of f at x naught times h, that little bit. So this was a formula that you used in Calc 1 to approximate certain values. Typically, the examples used were things like approximating square root of 2. So you could approximate square root of 2 with this. You could approximate some nasty looking things using this linear approximation and get really, really close approximations actually for relatively little work. Okay. Now, the idea is I want to apply this to graphs of two variables, or to graphs of functions of two variables. So I want to apply this So I want to apply this to a function of two variables. Okay. So how do I do that? This is the notion of tangent plane approximation. So linearization or linear approximation was tangent line approximation. This is a tangent plane approximation. So the picture is exactly the same as we just saw. The idea is that I have some graph of some function. Maybe it looks like this. All right. So here's my f of xy. And the idea is that near some point, all right, so this point is x naught, y naught, f of x naught, y naught. Okay, so near this point, I can already tell there is a plane, right, that approximates the value of this function that is so long as I stay near this point, right? So it will approximate the value of the function near that point. And that plane is, of course, the tangent plane. Now, unfortunately, I can't draw as good of a picture as I could in the plane. So the idea, the thing that I want you to think about, is imagine that I drew tangent planes to this graph at a bunch of different points, right? If I looked at it from the side, it might look like this, right? So the idea is imagine I drew a bunch of tangent planes all over, maybe on this side too, on the back side, on all of these humps, all over, in the valleys, wherever, okay? So all over, I cover this thing, I have tangent planes all over the place, okay? I could do the exact same thing, right? I could take the surface away, just leave behind the tangent planes. The idea is that you would be able to basically see what the surface looked like just looking at the planes. But of course, the benefit here is that we have replaced a surface, which is a very curvy, bendy sort of thing that's continuous, and we've replaced that with a bunch of planes, right, which are easier to compute with. They're more rigid objects, okay? And so the idea is I want to do the exact same thing that I did in Calc 1. So how do I do this? Well, if I want to compute, say, or if I want to approximate the value of a function near some point, then I have a little bit in the x direction that I might be moving. But now I have this other direction, right? So just to refresh your memory, here's what linear approximation looked like in Calc 1. Okay, I only had, of course, one argument here. I only had one variable to worry about, and so I incremented, right? And of course, this h can be negative and small as well, so I can increment or de-increment, right? So this is a plus or minus h, if you like, if you really insist on h being positive. But now I have another direction to talk about, right? So I have another direction. There's no reason to insist that I am incrementing or de-incrementing in the same quantities, in the same amount. And so I have two quantities, h and k, right? And we're thinking about these as small. So h and k are small. And so if I want to approximate this value, this functional value, that is the value of f at x naught plus a little bit, y naught plus a little bit, then I can do that by evaluating the function at the point x naught, y naught. And then what? Well, you can probably already guess what's going to go on here. If I bring back the Calc 1 formula, to approximate this value, this is the value of the function at x naught plus h, this little bit, times the derivative at x naught. Well, in Calc 3, I don't have the derivative. I have multiple derivatives I can take, right? One in each direction here. And so what do you think is going to happen? Well, it's exactly as you expect. I would have that this is plus f sub x at x naught, y naught times h. So times the little bit in the direction of x plus f sub y of x naught, y naught times the little bit in the direction of y. And that's it. Okay, so nothing more fancy than that is going on. Okay. All right. Now, this is very nice. So conceptually, this is a great thing that we can do. This is exactly the analog of linear approximation in Calc 1, which was a strong thing that you could do to actually, it's fairly low tech to come up with some approximations that were really close without too much hassle. So I'm going to do the same thing here. Unfortunately, in terms of applications, what we're mostly going to be applying it to are problems that might seem a bit contrived, because they are, but this is just something that is convenient to use, or maybe I should say amenable to hand computation, right? If you wanted to see more powerful applications, you'd need computations that would be better done on a computer. And so let's see some examples of this. So here's an example, and this is how these problems might show up. These problems might not show up as a use tangent plane approximation. They might show up in a hidden way. Okay, and so here's an example. Approximate by hand. So when I say approximate, I don't mean plug into your calculator of choice. So approximate by hand the square root of 3.012 squared plus 3.997 squared. Okay, so approximate that. And this is how this problem is going to show up. Okay. All right. And so, what do I do here? So first, why would I recognize that this is a tangent plane approximation problem? First, I noticed that this is a problem of approximating the value of a function near a nice value, right? How do I tell what the nice value is? Well, 3.012 is close to 3, and 3.997 is close to 4. And so really this is close to square root of 3 squared plus 4 squared, right? Okay, so this is the idea here. And the function in question, of course, is going to be f of xy is square root of some quantity squared plus some other quantity squared. Right? So there's my f. The x naught and y naught, to determine those, I just look and see what these things are close to. So 3.012 is close to 3, and so x naught is 3. 3.997 is close to 4, so y naught is 4. Okay. Once I determine what my nice values are, then that determines what h and k are, right? So what is h here? So h is 0.012, right? So that x naught plus h is this thing. And k is, here's an example of a thing that's negative, right? But small enough, so that k is minus 0.003. Okay. Let me see. Questions. When can you start expecting to see homework exam grades? Exam grades should be done soon. Homework grades should be, homework 1 and 2 should be done anyway. I'll check on those a bit later. So yeah, so you should have those back relatively soon. Okay. So then what is it that I'm doing here when I'm asked to approximate this? So now I have everything I need for that formula. Why is it minus 0.003? The value I'm using here is 4, right? It couldn't be plus because then this thing here would be 4.003, right? So this is slightly less than 4, right? And so that's why it has to be negative. Whereas here, this is slightly more than 3, so h is positive. Okay. All right. It's just h and k are whatever you need them to be. They're whatever tiny little value you have added or subtracted to the nice values. All right. So the nice value here is 3, and you have the difference between 3 and 3.012 is you've added this little 0.012 to 3. And the difference between 3.997 and 4 is you have subtracted this little tiny 0.003 from 4. Okay, and so I want to approximate. So I want to approximate the square root of 3.012 squared plus 3.997 squared. So this square root, I want to approximate this. But this is equal to f of x naught plus h, right? Y naught plus k, right? Because we've set this up actually. In fact, rewriting this is f of 3.012 and y of, or sorry, and in the y slot is 3.997. Okay. And so according to that formula, right, just following this explicitly, this is f of x naught y naught plus the x partial of f evaluated at x naught y naught times h plus the y partial of f at x naught y naught evaluated or multiplied by k. All right. And so in order to finish this approximation, I need to compute the x and y partials. Okay, so again, solving this problem means ultimately taking partial derivatives. Just like the last question, right? Find in tangent plane. What was the thing that allowed you to do that? Taking the partial derivatives. Every single problem that you have in Chapter 13 material is going to be solved by taking partial derivatives. Okay, so our function is square root of x squared plus y squared. So then what is the x partial of square root of x squared plus y squared? It can help to, if you want to use this as power rule, right? It can help to rewrite this as x squared plus y squared to the 1/2. In that case, what is the x partial using power rule and chain rule? this would be 1/2 times x squared plus y squared to the minus 1/2 times, this is following the chain rule, times the derivative with respect to x of what's inside. Derivative with respect to x of what's inside is 2x plus 0, right? So this is 2x. Rewriting this in a friendly way, this is, so the 1/2 and 2 cancel, and so what I get is x over the square root of x squared plus y squared. So that is my x partial. All right, similarly, the y partial, since this is symmetric, the y partial is the same thing except I have a y in the numerator. So this is y over square root of x squared plus y squared. Okay. Well, what do you notice here? What you notice is that plugging in my nice values, 3 and 4, yields a nice value. Okay. So what do I mean by that? What is f of 3, 4? Right? So when I plug in 3, 4 into f, what do I get? I get square root of 3 squared plus 4 squared, so that's square root of 9 plus 16, so square root of 25, which is 5. Right? And so what I get here is that this is approximately 5 plus, what is the x partial of f evaluated at 3, 4? Well, here's the x partial, evaluated at 3, 4. Square root of 3 squared plus 4 squared is 5. And x is 3, so this is 3/5. So this is 5 plus 3/5 times h, but h is 0.012. All right, plus f sub y, evaluated at 3, 4, is 4/5. All right, so this is 4/5. Okay, since y is 4 here, so this is 4/5 times k, which is minus 0.003. Okay. And so here is my very nice approximation. So you can leave it like this. What is this if you actually did these multiplications, wrote this out? This is 5.0048 is what I get. Okay, what is the actual value? So the actual value is approximately 5.00481. So this is really good. This is accurate to 6 places. Okay, so this is a relatively stress-free approximation, and you see that this didn't take us too much work at all, but it's pretty accurate. Okay, so this is the kind of problem that you'll typically encounter when you're actually being asked to do tangent plane approximation. So you will probably not be asked specifically to do tangent plane approximation. You'll just be asked, approximate this value. Okay, and that should tell you that this is what you have to do. All right. Okay, so I think that just about does it. We started at 11:03. It's 11:53 now, so that's 50 minutes. So at the beginning of class on Friday, I will do what is going to be this is the equivalent of our first derivative test from Calc 1, which will allow us to identify extreme values, right? Mins and maxes for a function of 2 variables. And then we will end this discussion with Lagrange multipliers. Okay, that will be the very last thing we do in Chapter 3, is dealing with Lagrange multipliers, which also allows us to answer questions about extreme values in another way. So anyway, I guess that's all for today. So on Friday, you can expect us to almost entirely finish Chapter 13. We'll have one more thing to do, which I'll finish next week. I'll go ahead and mention that next Monday's lecture will be recorded and uploaded, so it won't be given live. But that should be the last time that I need to do that for the rest of the semester. So next Monday's lecture will be recorded and uploaded at some point. It won't be given live, but after that, for the remaining lectures, everything should be live. But Friday's lecture will still be live, of course. Anyway, so that's it. I will see you all on Friday.